Good afternoon, everyone. I'm Reetik Sahu from the Center for Computational Science and Engineering in the Mathematics for Optimization and Decision Support in Computational Research Division at Lawrence Berkeley National Lab. And today I'm going to talk about my postdoctoral research on predicting daily groundwater levels with deep learning models. And Chango has nicely introduced my topic and given some of the results. And I'm going to expand more on them and talk about what needs to be done next and what's really needed in this groundwater or water community for using machine learning models. Before I again talk about the results, here is a precursor to the problem. So we know that in 2014, California released the Sustainable Groundwater Management Act, which required all the basins in California to improve their overall water health of the watershed, which lists there are multiple objectives like lowering groundwater levels, seawater intrusion, reducing land subsidence, not having surface water depletions, and all of the stuff. But to do this problem, this is a complex problem because we don't really know how to do this well, especially when we want to do it everywhere across California. I think if you all just Google this Google image search on San Joaquin electric pole, which lists this 9-meter depletion or the land subsidence problem, it shows how severe this groundwater depletion problem is. And okay. So then, knowing the problem, what are the other obstacles? Okay, the most important uncertainty that we deal when we deal with groundwater is how much water do we have in the future? We don't really know that. Along with that, we don't also know what is the future groundwater demand going to be. Like how much are people going to pump given that there is this much precipitation or there's this much temperature? Because temperature, water availability, all plays a role in how a crop can grow. If there is less surface water, then farmers are going to pump a lot more from the ground because the groundwater acts like a buffer. So here you see this is a plot that Chango showed. This is the groundwater level. The top figure shows the groundwater level in Butte County, while the bottom figure shows the cumulative. So we know that the drought was between the period of 2012 to 2017, and in 2018 they kind of said that California is now drought-free. So although you see this apparent drought in rainfall, the groundwater is a much slower system and it reacts much slower than with other meteorological variables. So people therefore tend to use groundwater as their buffer, like when they don't have the rainy days, they just use the water out. So now when we want to build when you want to talk about groundwater management for the future, we need to find out how are these groundwater levels going to change when there is another drought in the future, or what if there is more water? How are people going to react to it? And apart from that, like how the groundwater levels are going to change, we need to figure out what are the future watersheds that might be at risk from future climate change or different weather scenarios coming in. How have then people currently, what are the current approaches that people are doing, or the water managers? So currently they use these high fidelity models like mod flow, power flow that combines the physics and the observations. The physics of how water is moving under the ground, or how it's raining, how do the plants take the water from the soil, how that is evaporated out. So all these require extensive characterization. You need a lot of observations to even just build a simulation model, and along with that you need a high computing sources, and then to run the simulations you need a lot of time. So now when I talked about that we need to run a lot of what if scenarios of what's going to happen in the future, running these high fidelity simulation models is going to take a lot of time, and it's not feasible, especially for the groundwater managers who do not have access to such resources. So here our team's research is trying to provide this alternate solution using machine learning that essentially just takes the observations that are currently available in the normal federal and state agencies of groundwater and all the meteorological variables. We run the data through these machine learning models. It generates very cheap surrogate models, and using those surrogate models, you can then run several or like thousands of future scenarios and then come up with some kind of risk assessment of what's going to happen in the future. And these things can just simply run on a laptop or a desktop, which groundwater managers have access to and not the HPC systems. Okay. But now to build a good machine learning model, the most important part is data preparation. And when it comes to water, data preparation is not easy, and therefore you also have a site selection. So we look at saliness. It's a well area. There's a lot of groundwater pumping and agriculture in that region. And let's say if you wanted to build a groundwater model in this area. So this area has only 2 data points every year. It's before the summer season or the growing period start, and one after the end of the growing period, to show that before the water was pumped out and what happens at the end of the growing period after all the crops. So using these 2 data points, it's not enough to show how things are going to react in the future. So we cannot build a good enough machine learning model in saliness. So now let's go to Butte, which is another location. It's not as well irrigated, or it's not like a farming land as in saliness, but here you have groundwater level data at a daily time resolution. So that's how you see all these multiple dots. And this is just one plot. They have several groundwater wells over here. They have several groundwater wells like this, which have data at a daily time resolution. So that's why we said, okay, let's choose Butte County, California. They have a lot of data. We can get a lot of meteorological data and stuff. So then we used all this data. And as Django mentioned, you essentially have this neural network model in. You given your past observations of groundwater, temperature, precipitation, stream flow, evaporative transpiration, whatever data that you can relate your groundwater to, you try to give that much data at your available time resolution. And with that, you try to predict what's going to happen to the groundwater level at the next time step. I'm saying this word time step instead of daily. I'll come to that, why the time step is necessary. Okay, again, there are lots of choices, and in our group, we looked at all these 4 choices, and within each of these 4 choices, there are another 5 choices to look at. So instead of doing hand tuning, which I did for around 2 to 3 months, using Julie's and Django's work, we essentially built this automated algorithm to build the best neural network structure to make our groundwater prediction models. So we did that, and these black box optimization approaches. We have compared Gaussian process-based with radial basis function with random sampling, and all of them, as Django showed, work really well. Okay, so now a bit more description about our experiment. So as I said, the location that we're looking at currently for the results is the Butte County in California. We are using historical observations of groundwater level, temperature, rainfall, and there's a nearby stream flow. The nearby stream flow is really important because it may not really be feeding into the groundwater well, but it is an indication of what people might be doing. So if there's a lot of water around, people might just use the stream flow instead of pumping the groundwater. So there is some kind of correlation between the stream flow and how much people are using water from the groundwater. Again, we have data that's at a daily time resolution. The parameter that we're trying to predict over here is the groundwater surface elevation above the mean sea level. There are different things you can look at. You can also look at what's your depth to water table, and there are different things you could predict. But in this study, we just looked at groundwater level from above the mean sea level. Our data sources were California Data Exchange Center and the California Natural Resources Agency, which essentially means that our data is there's quality analysis and they're properly created data sets. Okay, so here is our first result. Again, we used our training data was from 2010 to 2014, and then we did the validation of a neural network, and we tried to build our best hyperparameters of our neural network during this between using the data from 2014 to 16. And I guess I should not turn this side. Okay. As you can see that the average RMSE root mean square error is less than 1 meter, which is about 10% of your groundwater level change. So from a mathematics point of view, a 10% error is really big. But when you talk to groundwater managers and you tell them that we have brought down the error to less than 1 meter or 3 feet, they are very happy. They just wanted to know if the groundwater was going up or down, but now we are saying that yes, we are we have put the bounds on how much you can do. And this even works for if even testing the data, testing a neural network out into further into future with the data that the neural network has not seen. So if you see over here, the 2010 to 2014 was part of the training, and the 2014 to 16 was part of the validation. And this was essentially like the drought period where the neural network was trained to learn that things are only going to go downhill. But from 2016 onwards, things improved. So the neural network in this case was still able to pick that feature that things are improving, and therefore it picks that it's actually better. This is actually not trivial, because when we tested some other neural networks, some of them actually continued predicting that the groundwater level is going to keep going down. So in this case, our multi-layer perceptron network proved to do really well. And the compute time of this whole process of building the optimized structure of the neural network and coming up with the samples and all these things together, it just took 2 hours on a desktop system. So this is good news, because now groundwater managers can then actually use our system. Okay, so we saw that it worked in Butte, but then someone else asked, okay, then are you sure it's going to work somewhere else? And then we said, sure, we can test it out. And then we looked at a second look, 2 other locations. One is in Shasta, which is also in California, and the third one was Rifle, which is in Colorado. And in both the places, the neural network does, it's okay. It's still good with respect to what's being currently done. And each of these places, Shasta and Rifle, have different hydrogeological properties. They have different watershed behavior. So you have to run this whole hyperparameter optimization on them to get their own set of lags. So Butte might have a lag of, someone asked this question, Butte might have a lag of 360 days. But it's the Rifle site here had a much smaller lag because of the particular location of where the river was and where the groundwater observation well is. So this hyperparameter automated system kind of helps in figuring out what's the best neural network structure and the appropriate lags for for any place for that matter. Okay, so this is the question to Lucas. What if you change your input? So it's very possible that when you go to a different watershed, one that does not have much data, you do not have any ground observations, but rather you only have these remote sensing data. How would this method really work? So again, looking at Butte again, on the left figure, we have the neural network prediction. This is essentially with the most optimized neural network structure of lags and everything. I ran the experiment, let's say, 50 times to see, is our model predicting the same thing over and over again? So if you have your input features as groundwater, temperature, precipitation, and your nearby stream flow, you see that the uncertainty band around the dark blue is the mean, while there's a light blue band around it, which is the uncertainty. On the standard deviation, it's much low. So when you have all these input features in your training data, your groundwater predictions are much better. So let's say now I just removed that, I say that, okay, I do not really have the rainfall data. I don't have any rain gauges in that particular location. I don't even have a nearby, there is a river, but I can't really give you the data because we are not measuring it. So what will happen now to our machine learning model? Can a machine learning model still pick up the necessary features to predict, or can it predict the groundwater level? And turns out it cannot. It actually performs really bad. So here you see this, although the mean is kind of still close, but you see that we see this huge standard deviation band around the mean, which essentially means that if I rerun or retrain my machine learning model again, I'll get a totally different result. So this means that we cannot trust what a machine learning model says when you do not give the right amount or the right kind of input data. And these are like essentially the 2 extreme cases. One where you have all these things on the right side, you have just groundwater and temperature. So you then bring it up together. So, and these are like some of the other test cases that I looked at. So if you had the top row is the groundwater, temperature, precipitation, river, and evaporative transpiration. Evaporative transpiration essentially refers to how much water, so it takes into account what was growing in that area, and so how much water is kind of getting out from the soil naturally. And along with that, you have all these other parameters. So with that is like the best amount of data that you could possibly give to predict what is happening to the groundwater level. And as you move further down, you start removing one feature at a time to see what's happening. And as you see, the relative error to the maximum change in the groundwater level increases. So, and there's also the last row is when you essentially half the training period. So instead of having like 4 years of training, 4 years of continuous training data, I just give it 2 years of data. What would happen? So here we see that the uncertainty, or rather the light blue band that was around the mean, that essentially increases. So in those cases, it's difficult to trust. It's possible that for a particular run on your machine learning model training, you get really good result. But if someone else were to repeat that experiment, you might not get the same result. This is from an analysis point of view. But what it tells to the groundwater managers then is that they need to build the appropriate data infrastructure to essentially improve characterization of their particular watershed. They don't have to build these high fidelity models around the watershed, but just data structures, data infrastructure that's enough to even just run these machine learning models to essentially bring down the uncertainty about what's going to happen to them in the future. Oh wow, this actually went by too fast. Okay, so in conclusion, okay, these are the future guiding questions. The results that I looked at, Butte, Shasta, and Rifle, were all at one particular location. So in the left figure over here, they refer to just one red dot in the watershed. But when a groundwater manager talks about the health of a watershed, they refer to the overall average health. So that means that they have multiple red points, each with their own observations of groundwater, maybe temperature, precipitation, and river flow or something. So now the question is, how do we then extend this analysis from a single point observation to a multi-point observations, or spatially distributed system? Do we then build a neural network model that can model at all the red dots simultaneously, or do you take the observations at all these red dots and then average them out and then build a neural network around it? So that's a question that we need to figure out. If you paid attention to the slides that I showed, I never talked about any human decision, like what was the land use, how much land area was being used to grow wine or almonds or wheat or avocados. The most important driver in a groundwater level is actually the pumping data. And it's surprising that no one in California wants to share pumping data. Not the electric company, no farmers, unless so only some people know, so nobody really knows. So without having access to this pumping data, how can we incorporate human use or some kind of human behavior into this? And one solution is land use data. So California, or rather most states in the US, they release an annual land use report, which essentially gives an annually average version of what crops they grew and what are the counties where the fruits or everything. So from that, you could technically backtrack what months these crops had grown and what were the areas. So you could in some way incorporate land use, but that's the work that needs to be done. Third is the question of what the what-if scenarios of the future. Now we all know that in the IPCC, the report, you have these two scenarios, the RCP 2.5, which is like the really nice scenario, and the RCP 8.5, which is like, yeah, things are going to go downhill. But how far in the future can we actually predict? In the simulations that I showed, I at max showed a 1 year or a 3 year simulation into the future. But can we actually, given these climate or meteorological variables of temperature and precipitation, can we actually run our machine learning models 50 years in the future? Or is it just only valid until 10 years and then we wait for 10 years to get the new data and then we again redo it for 10 years? So these are some of the questions that we still need to figure out as a research group. So, and here are the wonderful people in my research group. There's Julie Mueller, Deb, Reetik, and so that's me, Django, and Boris, Charu, and Bhavna from the Earth and Environmental Sciences. So if you have any questions, please visit us and we'll let you answer. We'll answer them, sorry. Thank you.
So let's say So if we predict that the levels of groundwater are going to drop consistently, what do you think could be a solution? Like just like pump less water, or like it's going to be a catastrophe?
The solution is obviously pump less water, or rather grow less almonds and grow less grapes to make wine and everything. It is difficult. So we did talk to people from the Department of Water Resources in Sacramento in California, for the California region. And one of the solutions that they were looking at is something called as managed aquifer recharge. It's called MAR without the Mars. And they were essentially thinking about the solution that, okay, let's stop the groundwater pumping, or let's stop growing crops in certain farms, and let's just use the rainwater and let it just drain into the ground. The problem with that is it's still going to take a long time, and the perceived benefit is it's not good enough. And most analysis or study that has been done on this is very local, or like it's only like maybe an acre or 2 acre of land area. But if you're talking about improving the overall health, we're talking about an entire watershed, and it's difficult. But yes, so yeah. To understand the severity, you should just Google that image of San Joaquin electric pole drought, and that will give you this nearly happy guy having this 1925 sign and this 1970, and then it goes down. It's 9 meters, which is about 30 feet of land subsidence because the groundwater has been removed from, and essentially the weight of soil itself just compacted the land itself, which is interesting. So it is a severe problem, in case you're not. Yeah.
Anyone else?
I got a quick question. So why are people hesitant to share how much water they're pumping from these watersheds?
Once I observe your action, I can then control it. So if you now share it, then you're now liable, or rather they can tell you to now control it, and then no one can. Yeah, people don't like it to be asked what to do. I think some counties have become now, like they are now saying that, okay, we need to change our action. So there are some counties which are willing to share, and we are still trying to get in touch with those, but it is still, like the PG&E, which is like a good example, like you have the electricity data or how much the consumption is, and you can figure out that if it's in a agriculture region, so you know that electricity is being used for groundwater pumping. But even that PG&E data is anonymized, and it's averaged to a monthly level over a much larger area. So it loses that we cannot tell what's actually happening over there. That would definitely make all these models and things really well, but yeah. But when it comes to also future, we need to figure out that the future, when we talk about the future scenarios, what we have is temperature and precipitation only as our input. We can't really say what else is going to happen. So yeah, there are lots of input features and data that needs to be built, that we need for building effective or robust machine learning models. So yeah, hope that answers it.
Thank you.
Anyone else?
I have another question.
Yes.
Yeah.
So the predicted values,
Yes.
If I understood correctly, are they based on predicted like precipitation levels?
No. So I should go back to that. Yes, that's a question that's been confused. So in this, when we are doing this 2-year prediction, we are taking in the observed temperature and precipitation and stream flow. So those were the observed data, while the groundwater that's being fed into this loop of the time loop, that's the past predicted. So the idea is that you always take in your input as the future climate scenarios of temperature and precipitation, and you make this groundwater level prediction day after day or month after the other. So yeah, so that's, yeah.